My talk will be about JavaScript 0, real JavaScript, and zero side-channel attacks. The outline of these talks is, first we do a short analysis of current microarchitectural and side-channel attacks that are publicly known that work in JavaScript. We identify building blocks for those attacks that we can mount them in the browser. And after we've identified the building blocks, we can actually start to design countermeasures for preventing attacks in JavaScript and implement the countermeasures and, of course, evaluate how they work and if they actually work. So first of all, we look at the landscape of microarchitectural attacks. There are currently 11 published microarchitectural and side-channel attacks in JavaScript. Microarchitectural meaning they exploit things like caches, they do cache attacks, or interrupt timings, row hammer, page fault attacks, and all that's on a microarchitectural level, and which can be exploited in JavaScript, as well as other side-channel attacks, for example, on sensors. And every attack requires some building primitives, some requirements that we can actually mount them. And we analyzed all of the attacks to find 5 categories of requirements, which are memory addresses, so that the attacks know something about the memory layout beneath, some timing primitives to get accurate timing, multi-threading combined with shared data, and access to some sensors. And every attack we have seen requires primitive from at least one of the categories. Some of them also require more primitives, but at least one building block from one primitive is always required for an attack. So let's take a closer look at these categories. For example, memory addresses. The JavaScript language itself does not provide any addresses to programmers. So a programmer in JavaScript has no idea about virtual addresses and, of course, not about physical addresses. But a lot of attacks require knowledge about those addresses to build, for example, cache attacks. And the closest thing we can get in JavaScript are arrays, because they're linear, and we could use array indices as some approximation of virtual addresses. And we can also detect where physical pages start by detecting page faults through timing attacks, because a page fault takes a lot longer than if you don't have a page fault, and we can detect that in JavaScript. For this, for example, we also need accurate timers, because we have to distinguish events with different timings. And timers are something we need for nearly all side-channel attacks and microarchitectural attacks. The good thing is, for an attacker, we don't need absolute timestamps, so we don't need an absolute time for most attacks, but it's sufficient to measure time differences. The accuracy depends on the attack. Sometimes it's sufficient to have a timing primitive that measures timing differences in the range of milliseconds. For some attacks, the more hardware attacks, like DRAM attacks and cache attacks, we even require timing measurements in the range of nanoseconds. Then another thing that we now have in JavaScript, which is quite recently introduced, is multithreading. So JavaScript got web workers that allows us to have real concurrency in applications to run things really in parallel. But the introduction of those parallelism in JavaScript also enabled new side-channel attacks that can be mounted due to the parallelism of the language. Because now we can observe things that happens in parallel, and we are not scheduled anymore. And with multithreading, we also got shared data, which was then introduced. Usually we did not have shared data in JavaScript as such, because without multithreading, shared data is not really useful, because we don't have anything to share there. But with multithreading, we also got shared data. There's one data type for that, it's a shared array buffer. And it's basically an array that can be used concurrently from multiple web workers, the threads in JavaScript. It's not enabled by default, so it's an experimental feature, but it's planned to be enabled. But with the recent events around Spectre, browser vendors all now think about not enabling it. So we will see whether this will actually be enabled at any time. And the last category we found for side-channel attacks are sensors. So we have JavaScript on mobile devices, on smartphones, for example, and there we have a lot of sensors, and JavaScript has APIs to access a lot of those sensors. And only some of the sensors require user consent. If you think about the geolocation API or the microphone or the camera, they require user consent to be used. But other sensors, such as the ambient light sensor or the accelerometer, they don't require user consent, and anyone can use them without asking the user. And it has been shown for every sensor that's accessible from JavaScript that it can be exploited. Even simple sensors, such as the ambient light sensor, can be exploited to mount attacks. So these are the 5 categories we identified in all the attacks that are currently published. And now we can, after identifying all these categories, we can start building defenses. And our defenses, they have to address all of the categories. So we have to prevent everything. And the best thing would be if our countermeasure is not visible to the programmer. We don't want to have the programmer do anything to make the web safer. That should be completely transparent, kind of the microarchitectural level of JavaScript, so deep beneath everything the programmer can see. And we have to do that for all of the categories, so that no building block can be built anymore, and all the attacks impossible, and hopefully also future attacks are really hard or impossible to build because we don't have these building blocks anymore. So for memory addresses, we have to ensure that arrays cannot be used as a replacement for virtual addresses anymore. So our countermeasures, we present different approaches in the paper, but basically we want to make arrays non-linear in the backend and always memory-backed, and we add some random dummy accesses for array accesses. And this already prevents many microarchitectural attacks that require exact timings for memory accesses or linear memory. And it also has a nice side effect, because if we don't have linear arrays anymore, then we cannot deduce anything about the virtual addresses, and the virtual addresses are often also used for browser exploits, so that makes them also a lot harder. For timing, a lot of browsers already reduced the resolution of the high-resolution timer in JavaScript, and this is the first step and was a direct response to the first microarchitectural attacks in JavaScript. But we have shown that only rounding the timestamp is not sufficient if the underlying clock is still a high-resolution clock. And then you can recover a higher resolution from the underlying clock. So there was a proposal by Vaticonda et al. To add for fuzzy timing that adds a random jitter to your timestamp. That makes timestamps still monotonic, but the clock edges are randomized, so you cannot recover a high-resolution clock anymore from that. For multithreading, the only real solution is to actually disable multithreading. Again, don't have multithreading, but this is not going to happen. So what we do there is adding random delays to all the message passing functions, just in the range of some microseconds to milliseconds. And this already allows to prevent a lot of attacks that rely on fast message passing between threads. And for shared data, the same is true as for multithreading. The best would be to not have shared data at all. But that's not going to happen as well. So we have to do something else here. We delay the access to the shared buffer, because some attacks, especially the high-resolution timers that are built with shared data, exploit the fact that we can access this shared data concurrently, reading and writing in a very fast way. So if we delay those accesses, a lot of those timers do not work anymore, which are the prerequisites for a lot of attacks. And that degrades the best timer we can build to a resolution of some microseconds. And for sensor APIs, first step would be to reduce the update frequency and the resolution of the sensors, because there's no need to poll like an ambient light sensor 1,000 times a second. And in the long term, sensor APIs should always ask the user for permission to be used. Because, as said before, every sensor is usable for a tag, even simple sensors such as ambient light sensors. Okay, so we now know how to prevent all those stuff. How can we implement that as an actual countermeasure? The best solution would be, of course, to have that in a browser core. But that would require all the browser vendors to implement that, which could take some time. Having a browser fork ourselves is hard work. Maintaining that takes a lot of time. And we want a generic solution. We don't want to have it for one browser, and we don't want to maintain a lot of browser forks. Also, having something like a proxy is hard because we have to parse JavaScript, and this is really complicated as JavaScript has so many features. So our solution is to implement everything in JavaScript with a technique called virtual machine layering. And we can actually implement all the countermeasures in JavaScript as a browser extension. And it works like this. In JavaScript, we can redefine functions, and we redefine the functions as a wrapper. And the wrapper then checks whether we can actually call this function or whether we have to replace or filter the result of the original function. And this is quite easy in JavaScript. We can just save the function pointer to the original function, overwrite it, and if someone uses it then our new overwritten function is used instead. The same is true for properties. We can also replace properties by such wrappers. And for objects, it's similar. We build proxies for every object, for every dangerous object, and this proxy proxies all the function calls to the original object. If we decide to filter some methods or remove some methods, then they're gone. Otherwise, they're handled by the original object. And this sounds nice, but as it's in JavaScript, it could be circumvented in JavaScript by an attacker, of course. So we also require some self-protection. And this also uses a nice JavaScript feature called closures. And we built this anonymous closure here that contains the original reference. And what we then have is that our original function pointer that we still use in the extension is only available to our extension and not in any global scope, so an attacker cannot access the original function. And by additionally freezing the object, the attacker cannot revert our changes to the JavaScript functions anymore. So we also protect our implementation. It protects itself. And we can show that it actually works. So there's a page border detection attack that's a building block for a lot of side-channel attacks. It creates a huge array, iterates over the array in JavaScript, and measures the access time for every access. And if a new page starts there, then we have a higher timing because the page has to be loaded from the operating system. And it looks like that. We can directly see where a new physical page starts. If we have our countermeasure with the random accesses, we can't see that anymore. We get random spikes at random points in time, and an attacker cannot learn anything about the addresses beyond the array. For multithreading, there is an interesting attack that allows to detect interrupts by creating time windows of equal size and just incrementing a counter within the time window. And if we have fuzzy time, then we cannot create the equally sized time windows anymore, and we get random events. So if we look at there's a smartphone with interrupt detection attack running, if we tap the screen with interrupts, we get a different amount of increments of the counter in this time window, and we can clearly detect these taps, these interrupts. If we have fuzzy time, that degrades to some random plot where we can't actually detect the taps. For multithreading, if we add our delay, then there's an attack that doesn't work anymore. It measures the latency of the event queue by posting a lot of messages and measuring the latency. And if you have high latency, then we know that there's a user input happening. And that stopped working. That looks like that. The spikes indicate a high latency, and there's a user input, and we can spy on keystrokes. And if we have the Somehow the clicker stopped working. No. Doesn't want anymore. Perfect. And if we have this message delay, we have these random delays everywhere, not just because of the user input latency. And thanks. And we can't deduce any user input anymore. The same for the shared array buffer with the delay. If we add this random delay to access the shared array buffer, then if we don't do that, we can measure timings in a really high resolution to detect cache hits and cache misses. If we add this, then we can't see anything anymore. So in the paper, we propose many of those defenses, and we show that if we apply all of them, then all the current attacks do not work anymore. And also for the user experience, we tested it in a double-blind study, and users were not even able to detect whether this policy, this JavaScript 0, was active or not. So as a conclusion, rounding timers is not sufficient. We need a lot of more protections, but they can all be implemented even in the browser, and they make the attacks make all of the attacks impossible, and also future attacks a lot harder. And we expect to see a lot more microarchitecture in JavaScript in the future, so we need these countermeasures to be applied. Okay, so thank you.
Hello. Hi, James Mickens from Harvard. So I really like this work. I share your opinion that JavaScript is the devil. One concern that I do have, though, is that there have been some other approaches to try to use this virtualization approach to create, in essence, sort of a sandbox at the JavaScript level. And a lot of those approaches have been very difficult to actually make secure because JavaScript actually allows a lot of escape hatches. For example, to find various aliases for sensitive things by looking up prototype chains and things like that. So how confident are you that someone who knows that they're running inside of your system couldn't do something like try to skip through prototype chains, find eval some way, and get around your system?
So it's a really good question, yeah. It's true, JavaScript has a lot of hacks and possibilities. We tried to find all or most of them, but there's still the remaining possibility that we missed something, that an attacker can circumvent it in some way. I also talked to engineers at the Google Chrome team about that, and they said, yeah, it looks okay, but I guess there are still some hacks maybe left where an attacker can get the original reference. So as I said in the presentation, the best would be to actually implement it in the browser core, because it's really easy, and we have to wait for browser vendors to actually implement it. But right now, for I would say, not a semi-motivated attacker, that should be quite secure what we have there. But I guess there is a possibility to still circumvent it by using prototype chains or something like that.
Thanks.
Hi, Ben Stock from TISPA. I have a kind of a mean question. You said you sampled user experience in the sense of they don't notice that something is going on. But can you comment in terms of performance degradation, like in real time measuring like the performance overhead? Because I've had papers criticized for causing 10% overhead in a browser, which for me sounds fine, but for engineers at Google, they said like, whoa, you can't do that. We spent like a year to get another % out of this. So just wondering what the percentage is there.
So we also did some benchmarks for the overhead, and it's quite low. So you have a bit of addition in the page loading time at first, because you have to load all the policies and apply them. But if they're applied, then usually it's even faster, because you don't have certain functionalities anymore. Okay. And so we had that in our user study, that people thought they were using not the JavaScript 0 extension, because the pages were faster, because with this, we blocked a lot of dangerous stuff going on in the background with all the tracking and stuff like that, and they made the pages even appear faster than without our countermeasures. Okay. So it's really hard to say. You have some overhead, of course, but it also appears sometimes faster, and the problem is also if you block the high-resolution timer, it's not that easy to measure the time anymore in the browser for benchmarks.
But you still have the reference, though.
Yeah.
Now I was just wondering about, especially if you have more page misses because you like randomize the access, whether this would cause some, well, measurable overhead.
Usually not, because usually if you have a benign application, then you don't have a lot of memory accesses all the time. So for a benign application, it's negligible what you have as a performance overhead. Of course, for a malicious application like a row hammer or a cache attack, you have a lot of memory accesses, and there it gets slower. But you don't care about malicious applications getting slower because they don't work in the end anymore.
All right, thank you.
Hi. Yeah, Nikos Vasilakis from the University of Pennsylvania. There are a lot of technical details I don't fully understand here, but you said, right, answering the previous question, that a lot of functionality was disabled, and I don't understand how were websites still working if there was functionality that we're using that you disabled?
So you don't remove the functionality, but usually you replace them. For example, the high-resolution timer, you get a timing resolution of microseconds from the browser, and that's usually not necessary. And if we add random jitter, and then we have a resolution of like 100 milliseconds, that's the same as a Tor does, the Tor browser, and still the pages work there. So many of those functions we remove or degrade are only used for tracking purposes or other things that the user actually does not want. But we don't completely remove functionality. Also for sensors, for example, if you have the ambient light sensor and a page uses the ambient light sensor, the page just returns constant values. And the page should still work if the sensor returns a constant value, because that should never be a requirement for a page to actually work, to have like the ambient light in an accurate way on the website. So for our tests, we tested a lot of websites, and we couldn't find a single website that broke down with the countermeasure.